In macro machining, material removal operations can be categorized in terms of the size of the individual elements of the workpiece that are removed. In this way, machining operations can be categorized into 1. Cutting processes, 2. Grinding and filing processes, and 3. Non-traditional machining processes. In cutting operations, chips are in the form of ribbons or particles with a thickness of about 0.025 mm to 2.5 mm. The main cutting processes are 1. Milling, 2. Turning, 3. Hole making, 4. Sawing, 5. Shaping and planing, and 6. Broaching. Milling is a machining process where a rotating tool is used to shape the surface of a workpiece. Milling machines come in a variety of configurations that range from 3 to 5 axis machines. They are among the most widely used CNC machines in industry. Among the most common milling operations are 1. Pocketing, 2. Contouring, and face milling. Here is an application of milling. The shown workpiece is being machined using a 5-axis milling machine. Turning is a machining process where a tool is used to shape a rotating workpiece. Turning is used to machine cylindrical, conical or helical features. Among the most common turning operations are 1. Profiling or profile turning, which is used to machine a combination of straight lines and curves into the profile of the axis symmetric workpiece. 2. Inner diameter boring is used to machine the inside of the workpiece. 3. Outer diameter turning is used to machine the outside of the workpiece. 4. Grooving is used to create thin grooves on the surface of the workpiece. These grooves are often used for retaining rings. 5. Threading is used to machine a thread onto the surface of the workpiece. 6. Facing is used to machine a flat surface that is normal to the axis of the workpiece. Shown are some applications of turning. The workpiece on the left is a threaded lead screw, while a short shaft is being machined on the right. Various hole-making processes are used to drill and finish holes. These include drilling, reaming, boring, tapping, countersinking, counterboring, center drilling, and spot drilling. All the aforementioned hole-making processes can be performed using either a drill press, a milling machine, or a lathe. When performing a hole-making operation on a lathe, the axis of the hole has to coincide with the axis of rotation of the workpiece. Drilling is used to make holes, but it is not a very accurate hole-making process. The holes made using drilling tools are usually not very accurate with respect to their size, straightness, or roundness. That is why drilling is considered to be a roughing operation. Hence drilling is often used as a first cut, to make a hole that can later be finished by another process such as reaming or tapping. Drilling accounts for roughly a quarter of all machining operations performed in industry. Reaming is used to finish holes and give them good roundness and dimensional accuracy in terms of the hole's diameter. Reamers cannot be used to open up a hole since they are unable to drill in the center of the hole. Hence reaming can only be used to finish a hole that was made using another hole-making process such as drilling. Since reamers tend to follow the axis of the pilot hole, if the pilot hole was not straight, the finished hole will probably not be straight either. For this reason, in order to obtain high-quality holes, the reaming operation should be preceded by a boring step to make sure the hole is straight. Reaming removes a small amount of material, but if the amount of material that is removed is too small, the surface of the hole can become burnished or the reamer can be damaged. It is hence recommended that for soft materials, such as aluminum, the minimum difference between the reamer's diameter and the initial hole's diameter should be 0.2 mm. For hard materials, such as steel, the minimum difference between the reamer's diameter and the initial hole's diameter should be 0.13 mm. The spindle speeds for reaming should be smaller than those for drilling for similar size reamers under similar conditions. The feed rate on the other hand should be 2 to 3 times larger than the feed rate for a drilling operation under the same conditions. Boring is a hole-making process that is used to enlarge existing holes to a precise diameter. Boring cannot open up a hole since the boring tool cannot drill at the center of the hole. Boring produces holes with excellent roundness and straightness. A single-point cutting tool is used in boring. The cutting point is the corner of a machining insert that is attached to the boring tool. Boring operations can be performed on both turning and milling machines. In turning, the cutting edge can be moved off-center with respect to the rotation axis of the workpiece. This is achieved by positioning the cutting insert tipped boring bar at the desired diameter where the cut is to be made. In milling, the cutting edge can be moved off-center with respect to the rotation axis of the spindle. This is achieved by mounting the eccentric cutting head on the machine's spindle and adjusting the radial position of the cutting insert. The radial position of the boring bar is usually adjustable within a certain range to produce holes of different diameters. The boring tool in milling applications must be symmetric or balanced to minimize force unbalance during machining. This is especially important for cuts performed at large diameters. Tapping is a machining process that is used to make internal threads within a pre-existing hole using a tool that is called a tap. The tapping tool is shaped in the form of the finished thread. The thread along the length of the hole is machined in a single pass. The tapping tool usually has 2 to 4 flutes cut along its length that carry the metal chips out of the tapped hole. Tapping is a very efficient process for threading small diameter holes. In order to correctly machine a thread using a tapping tool, the feed of the tool into the hole must be precisely synchronized with the rotation of the tap. The tool must stop at the end of the travel and then reverse its rotational direction before being retracted from the threaded hole. Otherwise, the tool will machine the thread away as it is retracted from the tapped hole. There are 2 methods of the tapping tool's rotational direction as it is being retracted from the hole it has threaded. 1. Using spindle reversal. And 2. Using a self-reversing tapping head. In spindle reversal, the tapping tool is rigidly attached to the machine's spindle. In this case, the spindle's rotation must be stopped at the end of the tool's travel and then the spindle must reverse its rotational direction when the tapping tool is being retracted from the hole. The main advantage of this method is that no extra special attachments are required. The rotation direction change is simply programmed within the NC code. This method, however, suffers from several disadvantages. It increases the wear and tear on the machine because of the required sudden stoppage of the spindle and the change in rotational direction. It increases the energy usage of the process since the energy associated with the angular inertia of the spindle is usually lost when the spindle is stopped at the bottom of the tapped hole. Furthermore, the spindle usually has to be stopped again after the tap is retracted from the hole. This is necessary to reverse the spindle's rotation once more to prepare for the next tapping cycle. Because of the high inertia of the spindle, the time required to decelerate and subsequently accelerate it, increases the overall tapping cycle time. A self-reversing tapping head automatically reverses its rotational direction upon being retracted from the tapped hole. The spindle of the machine does not need to change its rotational direction. The advantages of the self-reversing tapping head include reduced wear and tear on the machine, lower energy usage, and shorter cycle times. The main disadvantages of the self-reversing tapping head are its high price and the special method needed to mount the head on the machine's spindle to prevent the tapping head from rotating. Countersinking produces a V-shaped section at the top of a hole. This allows the head of a screw or rivet to be seated inside the workpiece. The most common cone angles for the countersunk beveled surface are 60, 82 and 90 degrees. The one shown here is 60 degrees. Since they are capable of drilling at the center of a hole, countersinking tools can machine a beveled surface either before or after a hole is drilled in a given location. A burr, in machining terminology, is a raised serrated edge that forms at the intersection of a drilled hole with the surface of the workpiece, or along the edge of a machined surface. A burr can be formed at the entry or exit point of the drill from the hole, or both. Deburring is the process of machining the burr away to make a clean surface. Deburring is often performed by means of a countersinking tool. A special countersinking tool called the cross-hole countersink, which is shown here, is usually used to deburr drilled holes. The intersection of a cone and a cylindrical hole forms the cutting edge. The cone is non-symmetric to allow the cutting edge to bite into the material without the rest of the conical surface rubbing against the workpiece. Counterboring is used to add a concentric cylindrical hole to the top portion of an existing hole. It is used to provide a place where the head of a bolt or a nut can be nested. A pilot is often present on the end of the counterboring tool to center the tool with respect to the existing hole. Counterboring tools cannot drill at the center of a hole, and hence require a pre-existing hole. Spot facing is used to smooth a rough surface at the point where a hole meets the surface. This provides a leveled bearing surface for a bolt head or nut to rest on. Spot facing is usually performed using a counterboring tool with or without a pilot on the tool's end. Center drilling is used to provide a short pilot hole for a subsequent drilling operation. The pilot hole guides the drilling tool used in the subsequent operation to the correct hole location. This ensures the drill used to subsequently make the hole does not drift off center while starting the hole. The center drill is short and rigid to minimize tool deflection and to ensure the pilot hole is straight, round and in the correct location. Spot drilling is used to make a short conically shaped hole. The hole can be used as a pilot hole for a subsequent drilling operation. The cone machined by spot drilling has a base diameter that is usually slightly larger than the diameter of the subsequently machined hole. This allows for a small chamfer at the edge of the hole. Sawing is a machining process where a piece of a part can be cut off using a circular rotating blade, or a reciprocating blade, or a band with cutting teeth. The band moves along a straight line within the cutting area, and is wound around two rotating pulleys, one in the machine's head and the other in the machine's base. Band sawing machines are more efficient than reciprocating blade sawing machines, since the movement of the blade is continuous, and does not need to be reversed, as is the case for reciprocating blade machines. There are two sawing processes. Straight sawing is used to make a straight cut in order to cut a piece of material such as a pipe or bar. Straight sawing can be performed on machines with rotating or reciprocating blades, or on band sawing machines. Contour sawing is used to create a contoured piece by cutting the part along a prescribed path. Contour sawing is primarily performed using band sawing machines. Shaping and planing use a cutting tool that moves with respect to a workpiece in a straight cutting motion to generate a flat surface. In shaping, the tool moves during cutting while the workpiece remains stationary. In planing, the workpiece moves during cutting while the tool remains stationary. Milling has replaced shaping and planing in many applications due to its higher production rates. Shaping and planing are still commonly used in some special applications such as the production of gears. Shapes that can be produced by shapers and planers include straight grooves, angled grooves, T-slots, and dovetails. Broaching uses a multi-tooth tool with each tooth cutting slightly deeper into the workpiece. The broaching tool hence progressively machines the desired shape into the workpiece by moving past the workpiece in a single stroke. The broaching tool can be either pulled or pushed through the workpiece. Broaching can be used to machine internal, or to machine surface features on a workpiece. These are some examples of shapes that can be machined using internal broaching. And these are some examples of shapes that can be machined using surface broaching. Broaching is usually a very economical and quick way to machine such shapes for large production runs that can justify the high initial cost of the broaching tool. In grinding and filing operations, the thickness of the particles that are machined off is usually around 1/10 of the thickness of the particles in cutting. The particle thickness in grinding and filing ranges from about 0.0025 mm to 0.25 mm.